At CECO-Environmental, we're proud to be your single source for pollution control. It's our mission to protect our shared environment, and we relentlessly pursue that goal by providing reliable products and services to tackle your environmental challenges. Purchasing pollution control equipment can be a complicated process, particularly when you have a system that requires many different pieces of equipment. However, our vast range of technologies and solutions for pollution control and product recovery can eliminate that complexity, lowering your total cost of ownership without sacrificing performance. Across a wide variety of industries, CECO helps ensure you achieve real results. No matter your need, CECO has you covered. Simplify your environmental initiatives with our CECO-Environmental family of industrial solutions brands. CECO-Environmental is a global leader in air quality and fluid handling, serving the energy, industrial, and other niche markets. Through innovative technology and application expertise, CECO helps you grow your business with safe, clean, and more efficient solutions that help protect our shared environment. We work tirelessly to improve air quality, optimize the energy value chain, and provide custom-engineered solutions for applications including oil and gas, power generation, water and wastewater, battery production, polysilicon fabrication, chemical and petrochemical processing, and more. To learn more, visit CECOEnviro.com today.
Welcome, and thank you for joining us today for CECO Certified Continuing Education Series. Today, we will be learning about biofiltration basics presented by CECO-Environmental. My name is Mary Rusnak, and I am the Marketing Manager for the Industrial Air and Fluid Solutions segment of CECO. And with me today is Thomas Brazel, our Director of Product Development, and Vern Bueller, Applications Engineer for CECO. While we wait for everyone to join, I'd like to go over some basic housekeeping items about our platform and also about the PDH certification. So just kind of taking a look, first of all, if you have any sound issues, hopefully you'll be able to at least read the slide here, check your media player, make sure that you're not on mute, look at the help widget, see if there's something happening there. And then worst case scenario, you can always log out and log back in, and often that will take care of any issues that you have. As far as the platform goes, at the bottom of your screen are multiple application engagement tools, or what I call widgets, that you can use throughout the presentation. All the widgets are resizable and movable, so feel free to move them around so you get the most out of your desktop space. You can expand your slide area, make it super large, or you can basically, make it smaller by clicking on the top right corner. If you have any questions during the webcast, you can submit them through the Q&A widget. And really, though, to keep ourselves on track, we're going to answer all the questions at the end. But you can basically submit your questions at any point in time. If we do not get to your question here during this presentation, which is a possibility because we often have quite a few, don't worry about it. We will definitely get to you after the presentation and make sure that question is answered. A copy of today's slide deck and additional help materials are also available in the resource list. We encourage you to download any resources or links that you might find useful, and all of these will actually remain available as well on the on-demand version. If you also take a look in the bottom widgets on the bottom, you'll see that we have ways you can actually, in the resource area, if you look, we have links to LinkedIn, YouTube, Facebook. We post all of our events on these, so feel free to follow us there, and that way you'll stay on track with everything that we offer. We have several events still here planned through June, and then also in the fall again. One thing for anyone who's taking the PDH portion and taking the quiz at the end, you're going to want to take a look at the biofiltration summary. That might actually help you out there a little bit. We're able to offer professional development hours in 36 states right now. And as I was talking about the widgets before, if you hover over them, it'll tell you what they are. So feel free to share via social, email us if you have any questions. And then finally, the last two widgets, which are probably the most important if you're taking the quiz at the end, the test and the tracker widget. The check mark will take you, basically that's where you're going to find out, you'll find your quiz at the test section, and you'll know if you've completed all the requirements at the track here location. So just again, webinars are bandwidth intense, so make sure that you close down any unnecessary tabs. This is going to help so that you don't have as much of a lag. If you do find that you're behind on any of the slides, push F5 on your keyboard, and that will actually refresh your page. I've also found that Chrome seems to work best here. There's also additional answers to common technical issues in the help widget, like we discussed before. An on-demand version of the webcast will be available after the event and can be accessed using the same link that you had before. All interactivity remains, including the testing capability. So if for some reason you accidentally get logged off or you have to leave, you can always come back in and fulfill and finish the rest of the presentation. So today's webinar is worth 1 professional development hour or contact hours. You must be present for at least 50 minutes of this presentation, and you need to complete and pass the test, which is basically finishing 8 out of 10. Remember those 2 widgets I was talking about at the bottom? When you're done, go to that certification widget, and the print certificate box will be available. That does not show up until you have actually completed all of the qualifications. So make sure that you fulfill everything that you need to, then you'll be able to go back there and print it out. At any point in time as well, if you can't do that today, you can also just log back in and print it out from the on-demand version as well. If you have any questions, just contact me. There's my email. You can also use the email widget at the bottom, and that will contact me directly. The webinar is 1 hour long, but we're going to keep the platform open for an additional half hour after the event is done to allow people to finish up the quiz and, print out any materials that they like. So in terms of an outline, I'm not going to go over all of this, but we're going to talk about what is a biofilter. What types are out there, where are they used, what's a good application, what are some of the design parameters and things that you need to know if you want to use it in your application, what does it look like, and just some basic comparisons to other air abatement technologies that are out there. So to kind of determine why this one would actually work for you. So we hope you enjoy the presentation, and we look forward to giving you this information on this green technology. We're going to start off with a poll question, and you'll be able to actually answer the question in the next slide. How much experience do you have with biofiltration? And there's a couple options there. I'm an expert, I have some experience, a little bit of experience, no idea what a biofilter is. And this is where you would answer. And we'll give everybody a couple seconds. Okay, finished up, and let's see what we have here today in our audience. For some reason, we're not getting any answers, which I don't think is right. Let's try that one more time and see if it'll freshen up here. There we go. Okay, so we have a good portion here that are learning about biofilters for the first time. Quite a few have a little experience. And then, we have some that, have some experience, but no experts. So I think that you'll get a lot out of this presentation. It's definitely geared to giving everyone that basic overview. So we're glad you're here. And I'm going to pass this on to Thomas, who is going to start with our first portion of the presentation.
All right. Thanks, Mary. I appreciate that. Oh boy, I don't know if we're both clicking. Okay. Yeah, so that poll results, there we go, we're aligned. Sorry about that, everybody. Yeah, the poll results great. I'm glad there's no experts here. Seems like we have the right group of people that hopefully we can get you guys a little bit of framework about what a biofiltration system looks like and how to use them and where you should consider them. And so with that, let's jump right in. So first question, what is biofiltration, right? So in the context of this conversation, we're really talking about gas streams, air streams from a process where it has some sort of compounds, VOC, something similar, where we want to treat that VOC or the pollutant. And how we're going to treat that, we're going to treat that with microorganisms in the system to degrade and biooxidize the compounds to make them suitable for emission to the atmosphere. And you can think of it as a kind of a two-step process. The first step is transferring the compounds you want to treat into the biofilm where the biology is living. And then the second step is the actual biooxidation that occurs within the biofilm. And so then, and we're going to go in a lot more detail about what that is and why, what parts you should care about as an engineer or someone that's involved in one of these systems. And so why would we want to use a biofiltration? Well, it's a green technology. I'm sure you saw that in Mary's blurb she sent out to everybody. And we're really excited about it because it really is a green technology. And also green sometimes also means reduced cost in this case. And so how are we green? How do we reduce cost? The first thing, a lot of the competing technologies out there for this application use a lot of energy. A lot of times it might be natural gas, for example, and natural gas has combustion gases, right? So we might be treating A problem but creating a little bit of B. This one doesn't do that. Biofiltration does not create NOx. It doesn't have a particulate output. It doesn't produce CO. It's much more greener in that environment, that aspect. That energy thing I just talked about also helps with OpEx, right? So we spend money to buy a piece of equipment, and then we spend money to maintain and operate it. So when you compare a biofilter where you don't have to inject natural gas, for example, that's obviously a cost savings. The pumps, the air system, the delta P across it, typically you'll see less energy, and Vern's going to go into more examples of that in the second half of the presentation, but often the OpEx is lower than other technologies. CapEx can be lower. It really depends on what your emissions are, what your permits are, how big your footprint is, things like that. Sometimes it can be a little more, sometimes it can be the same. We like to say it's less. We are the biofilter folks here talking. In many cases, it is less. Typically, what are we trying to treat with it? Organic and inorganic compounds. Vern will get a little more details of what is a good thing to be using a biofilter. It's not a one-size-fits-all. You can't treat everything with it just like anything. And so we think it's a great thing to know about because it should be in your options when you consider an air abatement technology. Typically, you're going to see biofiltration from the air side in municipal and industrial applications. A lot of people, probably the people that have a little bit of experience, probably knew it from municipal applications. For the context of this, we're going to talk mostly about industrial applications, although really the fundamentals here carry over to municipal. And we have a couple of little municipal topics sprinkled in here and there. If you have more questions specific to that, you can certainly put it in the Q&A. And as Mary said, we might not get to it today, but we'll definitely follow up and can answer any of those questions. So biooxidation, that's the heart of what biofiltration is, right? And it's a biological process. We're typically treating VOCs. Some other compounds are also can be considered, but really you're introducing them to a biomatrix, and then you capture them there and you digest it. And from this digestion, you're turning the exhaust into carbon dioxide and water vapor to the atmosphere. So obviously that's a fine thing to send compared to a VOC. And so that's the heart of the process. You can see this picture on the top right. That's kind of the chemistry, the biology background of you got the air on the left and you got the biofilm on the right, and there's a mass transfer process across that. And you're slowly converting things from what you don't want to what you want. Bottom, you can see kind of a nice little animation of what a system looks like, and inside of it you got the microbes, right? Those of you from biology class remember you've got these different microorganisms that consume and eat and do things like that. Everyone, I think, probably realizes that living things, they need things to live. So you need food, you need energy sources, and you need nutrients, right? So it's like your yard. You go out and put fertilizer in your yard, nitrogen, phosphorus, other minerals. You want to make sure you have all the necessary building blocks for the biooxidation to occur. This is where it gets interesting. Some processes, they have a complex stream where they have that really can meet most of those needs, and you don't have to do really any or very limited supplement of nutrients. And sometimes you have to add a lot of nutrients. That's where you do testing, and Vern, again, will talk about testing, and you can figure out what you need to do. So that's biooxidation. I'm going to show you this next slide. So let me just quickly say I'm a mechanical engineer. I am not a biology person, but here's the summary of what's out there, right? So we talked about biology, but what is it? It's bacteria. There's different types of bacteria, and there's fungi. And I think the takeaway here is to really understand that there's not one size fits all, right? So if you're trying to get something that's a hydrophilic compound, and it's easy to get into water, and you can get into a slime, a biofilm, then a heterotrophic bacteria might be a great fit. But if it's more of a recalcitrant or a hydrophobic compound, or more complex or challenging to consume, it might not have enough time to get into the water. It might not be practical to make something for scrubbing that's so large. So you might use a fungi-based approach. And the fungi have surfactants and different enzymes that basically reach out and grab the compounds and let them work. So there's these different heterotrophic, autotrophic bacteria. Some systems we'll talk about are hybrids. They have a little bit of everything. It really depends on what you're trying to treat and how much space you have and what your permit is. And we'll talk about permits and what we're trying to treat. That's the biology. At the heart of this, again, it's microbiology. It's really the bugs. Potatoes work here. So let's talk at a high level for industrial applications. What kind of systems are there? What does a biofilter look like? Let me say this one caveat here before we get into this too far. There's a lot of, sometimes it's semantics, right? A lot of people call one thing a biofilter and thing a bioscrubber, or they call it all different things, and they might be meaning the same thing. For this presentation, if you want to learn more, the EPA have a great PDF out there about biofiltration. It talks a lot of this information, some more details, and points you in great ways to learn. We use the naming convention they use there. And this kind of goes from left to right in age of development, from oldest to the most recent, and in complexity. And so we start on the left, a biofilter, one of the earliest designs, on the order of 100 years old kind of technology. We'll talk a little more details, but it's the simplest one. You basically take the air emission, you use a blower to put it below the bed, and it goes out through the bed and gets treated. And you have biology in that bed. If you don't have as much control, we'll talk about pros and cons there in a second. Then we get a little more complexity, talk about a biotrickling filter. You can think, for those of you that know wastewater treatment plants, it's a lot like a trickling filter, except for where they have it in water. Here we have it in air. Similar concept, a lot of carryover. Those of you that know about chemical packed bed scrubbers, similar to that. The third one on the right, we're calling it a bioscrubber. And that is the next step up in complexity. And that is more about, you have a scrubber, and the goal is to get whatever emission you're trying to treat into the water. And then once it gets into the water, you put it into a large sump, and that sump has different equipment to treat the emission, right? So you do the oxidation kind of away from the scrubber in this sump. Now the sump might be at the bottom of it, or it might be off to the side. And this is intentionally, I showed a pretty complex flow path. There's a German standard, a VDI standard out there about bioscrubbers. It's very interesting. It's got a lot of good details there. But you can see there's different levels of clarifiers and fixed beds and different ways, aeration to treat it. And that certainly has its place. And then we show the bottom right. We're calling that a hybrid system. This is, from our perspective, an interesting approach to things. We see this in different spots. And this is basically saying, let's look from these different technologies, and one might be good for a certain compound, one might be good for another compound, but what if you have both compounds, right? So how do you integrate these together? And that's what a hybrid system is, right? You have maybe chamber 1 does hydrophilic, and chamber 2 does hydrophobic, or you need extra retention time so you can size the chambers appropriately. Gives you a little more control for combining technologies. And basically the takeaway here is there's a couple different ways to skin this. And what you need to look at is you look at your emission type, your permit requirements, and operational considerations. For example, the top left one, the biofilter, you might be somewhere remote and you just don't have a maintenance crew there, and it's the simplest to run. You just kind of let it go and you don't have to worry about it too much. But then you might be somewhere where you're more in a bigger city and footage is really a premium, and you might want something like the bioscrubber, and you already have a maintenance crew there. So you got to look at all your considerations. So let's dig a little bit deeper into the system types, pros and cons. So again, biofilter, here's a great picture on the left of one being installed. You can see there's actually 4 different sections here. So they're cheap to install, right? You can see it's basically looks like a drainage system. You're going to put some sort of media on top. A lot of times the media is organic. So that media would look like things like mulch or compost or different bark, things of that nature. As I mentioned earlier, it's simple maintenance. There's just basically a blower. Not a lot to take care of. The one caveat to that is media replacement. It's an organic media. We'll talk a little bit about channeling in a second, but that organic material can get used up. It can clog. You know, you can get too much biomass growth because you don't have a lot of control. And so you have to replace it typically in, let's say 2 to 5 years is a range to be thinking about. And it's not a simple change, right? You can see how large this is. It takes a couple of weeks to switch that out. So it's good to just to think about that in your planning. Another thing to consider, it actually can do very well in DRE on certain types of things. Again, you've got to know pros and cons of different things. You can get different types of bacteria and fungi growing in these environments, and so you can do very well because they typically have high retention times. And that's the next point, right? Retention time. So you'll hear the term EBRT, empty bed residence time. It's basically how long is the air in the media, right? So it's a biological process, right? More time, just like a thermal oxidizer, you need to have enough time for the oxidation to happen, or a thermal oxidizer might happen in a second or less. Here in this system, you're looking 30 to 90 seconds. So they're big systems, right? They're very large systems. And that's something to think about, again, when you're looking at different systems. Some challenges that we see with biofilters. So as I mentioned, these were the early designs, 100 years old type time frame. You still see them get installed today. They have their place, but they do have challenges. Typically, they're large fields without a roof, so it can be a little tricky to really know removal efficiencies. You could obviously put a roof on it if you chose to. That would kind of cut into your cost advantages, but that's one of the challenges. Surge loading efficiency, you typically don't have the ability to dump something into a sump. You don't have the ability to take any, you grow the biology for what you've got coming, and if that changes dramatically, the system can have a trouble. Footprint, again, you can see here's another great picture. It's huge. They're really, really large. Again, that's practical in some places, but not all places. And then the one other thing that's really interesting is bed compaction. So we see this picture on the left. It's mulch, right? It's compost. It's organic. Things are changing. So the bed will settle over time. You'll get channeling, right? We see channeling in other. The emissions are going to go out the channel and not through the bed. And when they go through the channel, you're going to have really low DRE performance there. And so that really starts to impact. And that's why the media replacement cycle, 2 to 5 years, is something to be aware of. So let's go to the next phase of the step in technology. So biotrickling filters. So we just talked about some challenges here, and as folks were designing systems, they looked at, okay, how do we solve these problems and what else is out there? So as I mentioned, wastewater treatment plants, they have trickling filters. They are all about treating material that's in the water and pouring the water over media and letting biofilm grow in that media. This is very similar concept, except for we got to get the emission into the water as part of the process. So how do we do that? We basically take a chemical scrubber, which is all about getting air emissions into scrubbing water, and then a trickling filter, which is about treating water that has stuff in it, right? So it works together great. It has inert media. The top right's pictures of 3 types of media. Good example. We have fixed film on that left, corrugated looking plastic. That's very commonly used in the trickling filter space. To the right of that, we have like random media or packing balls. Very similar to chemical scrubbers. You're looking for places for biology to attach. You're looking for drip points. It's very similar concept of scrubbing and letting stuff build up on it. And then the top, it's a puff of foam media, and that is useful in places where maybe growth isn't as excessive, not worried about plugging it, but you need lots of surface area. So it depends on where you're going. And that's where you should work with whoever's designing the equipment to understand the emission and the application to pick the right kind of media. They have pros and cons. The corrugated media has very low delta P. It's very good for certain aspects, but you're not going to get as much surface area or efficiency as the foam, for example. So another thing that's really common, or as part of this bio-trickling filter aspect, is the continuous irrigation, right? So we're spraying water over the top of the media all the time. And generally, these are countercurrent flow paths. For those of you that aren't familiar with scrubbers, that basically means the air is going up and the water is going down. So they're flowing countercurrent to each other. And what that means is with irrigation, you get a couple things. One, scrubbing, as we talked about. So that's about getting the emissions into the water. It's also about keeping the proper moisture in the system. So biology, just like your grass, your yard, right, your plants, needs moisture. You want to keep it in the right range. Nutrient supplementation. So I didn't talk about too much on the biofilter side, but that organic material in the media, that's a lot of the nutrients. So it's very hard to add it. Once it's gone, you really got to put new media here. Here, because the media is inert, that's not giving you any nutrients, but if you need to add nutrients, you can basically just inject it with the irrigation water. And then also biomass control is another thing that you can turn some knobs on flow rates and irrigation rates and nutrients and other chemicals to control the biomass. You want to have enough to treat everything, but you don't want to have so much that it overgrows and you can't flow through it. So this gives you one more knob to control. Again, biology is on the media. From EBRT, that residence time we talked about earlier. So remember the last one I said, I think I said 30 to 90 seconds. So it's much higher. Here, we see them as slow as 2 seconds. 2 to 60 is kind of a common range. So you can imagine the cubic feet of media is much lower on this kind of system. So that's a nice advantage. There are no free lunches, right? So what does that mean? Increased operating costs and maintenance. So we've got some more pumps to deal with. You might have to clean the media out. It might not have to replace it, but you might have to clean it out. You probably have some sensors. Vern will go a little more into the instrumentation, but those sensors need calibration, right? They need maintenance and cleaning. The pumps need a filter basket, for example. So there's just steps of maintenance. Nothing crazy, nothing that a plant, a facility that has a maintenance team can't do. We regularly see these things lasting 15 years without really any major intervention. And the bioscrubber aspect, or the scrubber part of it, really targeting water-soluble substances. So let's talk about the third kind of subset here, bioscrubbers. Again, that's kind of, we're going down this journey of complexity or development in the technology. So bioscrubbers is the next one. So basically, you're adding a sump to a bio-trickling filter to add more biological activity, right? So you don't add it in the media, you add it in the sump. And the sump can be a tank, it can be other industrial wastewater systems, and it's all about treating. It gives you more control, more options, change the temperature, do different things, add chemicals, refiners, clarifiers, things like that. There's a lot of options here. And so it's all about the sump, right? Again, it's water-soluble compounds or substances. It's got inert media. You have all the same ability with continuous irrigation, which is nutrient control, scrubbing efficiency, biomass control, things like that. Again, that no free lunch comment. That complexity comes with performance, but it also comes with cost and maintenance, right? So you've got more equipment to maintain. In general, these are well-vetted technologies from the industrial wastewater space, so it works well. It's not too hard to deal with, but there is more to take care of. So we're always advancing, right? The goal is to how do we do better? And we're going to talk about the hybrid. I mentioned the hybrid is kind of a fourth thing. And how did the hybrid come up, right? The hybrid approach, or what we're going to talk about in a minute. It's all about removal efficiency, right? So I talked about earlier different types of compounds. How do we separate how we treat them, right? So we're talking about step one, separation, which is partitioning hydrophilic and hydrophobic compound treatment methods, right? So treat one, then treat the other. So the hydrophilic removals, typically number one, so you have something that's a scrubber or something similar, or a bio-trickling filter chamber, and that gets the hydrophilic. And then you have some emissions that are going to come out to the next phase, and you want to put in something for hydrophobic. And so that's the fungi and the other types of maybe longer retention time, things like that. So that would be the next chamber. And then the other takeaway from this is recirculation. So we have different biology, but we need nutrients everywhere, and there's always value in kind of stirring the pot when it comes to biology. We're trying to re-inoculate often, right? Because because microbes don't live forever, right? You're always trying to grow more. So recirculation of the sump water between the two gives you the ability to control what's growing or help growth in the multiple chambers. Let's see, so I don't know how, here's a poll question. Mary, I guess, do I read this? So I'll read it. How's that? Poll question. Is your company looking at greener technology?
Go ahead.
I can read. I'm good at reading, I think. So
all right.
Is your company looking at greener technologies or other carbon footprint reduction initiatives? So this goes from yes, we're doing them right now, to yeah, we know it's coming in about a year. It's a couple years off, or no, it's not really on our radar. So I'll click to this, and I'll let Mary, you can go to the next slide when you think it's time.
Okay, we'll just give everybody a couple of seconds here to answer, and just, you know, kind of curious on where everyone's at with some of their initiatives. We'll give it a little bit more time since the last poll question seemed to take a few seconds to catch up. So, all right, let's see what some of these answers are. We've got a wide mix here, I think. You know, some at this point don't have anything planned, but, you know, definitely, you know, a decent amount that are already in the process of doing something. Quite a few, about 10% there that, you know, are within the next year, and then within the next couple years. And that's definitely what we're seeing, I think, across the board with a lot of companies, that, you know, there's definitely a move to, you know, looking for greener technologies and trying to figure out how to reduce their carbon footprint, and, you know, timeline that makes a whole lot of sense. So thank you. Comments?
Yeah, that's great.
So
and
back
this,
to you again.
Yeah, this certainly aligns to it. So a couple quick things. We were talking about the hybrid. Here's an example of a hybrid system. They exist in industrial space for a couple decades now. They're a great technology. This left one, you can see one installed, and the right graphic shows kind of the workflow of there's one chamber on the left and there's one chamber on the right, and Vern will go a little deeper on that. Again, it's all about VOC, getting more of the VOCs. Sometimes you're going to have hydrophilic and hydrophobic, and so you need an approach that addresses both of them. I think we have another. Yeah, so here's a little zoomed up picture of it. So it doesn't have to look like only one format, right? So there's a horizontal one on the left, which is great if you have a footprint. Then you have a bigger unit maybe, because it doesn't get too tall. And then if you don't have as much space, you can do it on the right, which is you're stacking the systems, right? So air is flowing from bottom to top, and you can see, if you squint, that says bio-trickling filter on the bottom and biofilter on the top, right? So that's the hydrophilic on the bottom, and then you're going to get the hydrophobic on the top. And more about it, but there's ways to get organic media in that biofilter to help growth of different types of biology. And so a couple last points before I hand over to Vern to get more in the details. Where would we see biooxidation applications fitting in industrial applications? So we've seen them installed in the last, again, couple of decades in a large area of the industrial space. Engineering wood is really honestly the biggest one. Very common there. It's got a really good use case there. But we see it a lot of places like paint coatings and resin applications. Anything that's thinking about an RTO or a thermal oxidizer, there's probably a good fit here, or it's at least considering a good fit. It's not. There are definitely some nuances here that should be considered. Not all compounds are conducive to biology growth, but it's something to consider. So here's a bunch of options. As you can see, they're kind of a broad spectrum of the industrial space. And then let's look at a couple more slides here about what an industrial installation looks like. So here's a paint manufacturer, and they were trying to treat hydrocarbons from the mixing process. And just to give you some scale, this is a 20,000 CFM system. It's a combination of a bio-trickling and then a biofilter stages. And so it's frankly not the smallest thing ever, right? They're big. But what was interesting here is this is a biofilter, but it's modular, right? There was a conversation about the paint process might be changing, or the manufacturing process would be changing, and they wanted to treat some different compounds down the road, and the fact, and that gives you flexibility. It's a nice thing about being modular. You can add chunks as needed if your process changes. And again, as I mentioned, we're talking industrial today, but just to give a little awareness of the municipal side, I think people are probably somewhat aware of headworks and pump station systems. These are the typically smaller. There's a lot of these out there. They often are bio-trickling filters and sometimes biofilters. They're typically a little simpler, lower maintenance. They do really well in that space. And so with that, I'm going to turn it over to Vern to really dig in a little bit about what makes a good biofilter and some of the engineering technical details to be considered with that. So Vern, if you want to take over.
Very good. Thank you, Thomas. Can you hear me? Hello?
Yep,
I sure can. Yep.
Okay, very good. So as far as what makes a good application, we can look at both municipal and industrial. And as far as what we like to see, because this is a living system that we're using to treat our contaminants, we like to have then continuous operation. So whatever the emission stream is that we're going to be treating, it's best if it's continuous. And that kind of gets away from then not having a feast and famine type scenario. So because it is a living system, we want to avoid where we're not going to having food or the contaminants going to it. And ideally, as far as the amount of contaminants and the concentration, the loading of these contaminants, high to low, we don't like it if it varies more than like a 3-to-1 ratio. So ideally, it's consistent, and then we don't have high peaks in the contaminants that we're going to be biooxidizing. The next is just because I'm going to say it's easier, is if the contaminants of concern are hydrophilic, meaning more water soluble, then that's going to be, we know that's going to be easier for us for the biology then to do their job. And we'd be looking at the bio-trickling filter in that case. The next is the airstream. The biology likes it when it's warm. There's two different ranges, but there's a range of 80 degrees to about 115 where the biology can live. Then there's a warmer range, 125 degrees to 150. And if we go above that range, then there's an issue. And finally, another thing that makes for an ideal application if there's no or very little particulates or solids. And if there are particulates or solids, then that's something that has to be dealt with. So if we run into a situation where, like, for example, if there's low temperature, then we can still perhaps consider using a biooxidation system, but we're going to have to then take steps to bring that temperature up, such as literally heating the airstream, or perhaps we can add temperature to the sump. And if it's too high, the temperature is too hot, if there's an emission streams that we want to consider biofiltration, then we're going to have to perhaps use dilution air. Particulate, if you have a stream that has too much particulates, then you're going to have to remove that with pre-treatment in front of your biooxidation system, such as a Venturi scrubber or perhaps a dust collector, but just to get the particulates out so that we're not having an issue perhaps with the media and plugging the media with the extra solids. And then finally, not that, as far as hydrophobic compounds, those less water soluble, those are not as easy, but we can still treat those, and Thomas has already talked about that. It's going to end up, simply what we are going to look for is more detention time. And quite often what we need to do, and this is more for industrial applications, would be some piloting in order to really hone in on what kind of times do we need to meet our objectives. And we have done a lot of talking on these hydrophilic and hydrophobic compounds. And I like this slide. This is representative of a 15-second bio-trickling filter. And what we can see here is the hydrophilic compounds at the top of the table are just more readily dissolved in water, and we achieve higher destruction during that time period. Other less water-soluble compounds at the bottom of the table we don't do as well with those. And again, that has to do with the fact that we're not able to get those hydrophobic compounds into the water as easily, where then the biodegradation can take place. And quite often, if we start looking at compounds that we know are less water soluble, then we want to consider piloting. And due to the fact that more likely than not, it's going to be an industrial application, because the municipal emissions that we use for biofiltration, those are the emissions are pretty standard, regardless of what wastewater treatment plant, municipal wastewater treatment plant you're at. But there is, as far as industrial, then quite often we'll end up having a matrix, a soup mix, if you will, of compounds that we need to consider. And sometimes you're not always going to be 100% sure of the effect on the biology until you do that piloting. So that, in addition to determining and trying to quantify then the detention time that you need, and that ties in then with, and you can see here, when you pilot an emission stream, you're able to get some valuable information as far as what are the optimum parameters that I need. What is that detention time, and that we can use then in order to meet our objectives. As far as the data that we want to get with the pilot, it's going to be very important, of course, to define your objectives, and that's going to come into just knowing, what do I need to meet, with this biofiltration unit. And once you have your objectives and goals defined, then based on some of the information that you know of the emission stream, you can then select the type of biofiltration unit that you want, be it or what a pilot does allow you to do is investigate and vary perhaps the detention times, and to see what works in order to achieve those removal efficiencies that you need to get. And it's important then to collect the data, just so that you can define success with what you've done. And I like this photo basically shows then pilot scale pilots, and the benefit of a pilot scale pilot is the fact that you are doing the pilot testing on the actual emissions to be treated. And one can, the alternative would be to do a bench scale pilot, which literally can be on a lab top bench. But again, pilot scale testing does give you the opportunity to do real world emissions and investigate then the treatment scheme that you're looking at. As far as design parameters, there's a range of parameters that one would initially consider. And for a biooxidation system, generally you're not going to want the compound loading, or the range of compound loading is going to be 10 parts per million to about 500 parts per million. And again, this is a guideline. The next, for biotrickling filters and bioscrubbers, the detention time is perhaps 15 seconds or less. For standard biofilters, as Thomas was saying, the EBRT could be 15 to 60 seconds, and then for some industrial applications, it may be longer, perhaps even over a minute. The gas velocity that is readily used for these various biooxidation systems is quite often 50 feet per minute or less. Another design parameter that we have to consider, regardless of the particular biooxidation system, is the irrigation rate. And that's going to vary from 0.1 gallon per minute to 0.1 to 1 gallon per minute per foot squared. And that foot squared is then the surface area of the media. So, and then in addition, there's also pH the pH is actually more of a process parameter in comparison to a design parameter, and that the pH more results from the biology that you use. And that's similar then to temperature. Temperature, we know perhaps that based on our emissions temperature, the design biology that we want to use, but it is actually the biology itself that will say, well, this is the temperature that I'm going to be at. And here we can talk, as far as those temperatures, there's two real classes of biology that we'll look at for these systems. And one is the higher temperature range, which is the thermophilic bacteria. And those range require a temperature. They thrive in an environment from 125 degrees to 155 degrees. And then the other class of microorganisms that we will consider are the mesophilic organisms. And those do well in any temperatures between 60 degrees to 80 degrees. As far as the parameters that are required in order to control the system, what we look at then for a biofilter, you can see that on the image on the left, the biofilter really has only one rotating piece of equipment, and that is the fan. So, and then the other thing that we're going to get into a little bit more is the biotrickling filter. So as far as the process parameters for the biofilter, what what we're going to be measuring and need to quantify with the biofilter is the gas emission flow rate. And this year it's going to measure by using an inline velocity probe, and that would be then configured for your particular duct dimensions. And there's also, you can also use pressure as an indicator of your flow rate. Another process parameter for biofilters is the irrigation flow rate, and that's going to be closer to the 0.1 gallons per minute per foot squared. Biofilters are going to require lower irrigation flow rates, and the irrigation most likely, it's going to be on for a set period of time followed by an off interval. The objective for a biofilter for the water side is to keep the filter bed moist and optimize the performance of the fungi and bacteria. So continuous irrigation of a biofilter may be detrimental if it flushes the fungus away. And then as far as temperature should be monitored with your biofilter just to assure that the media bed remains in the temperature range selected. Either that mesophilic range, 55 degrees to 115, or the thermophilic range, 125 degrees to 50. And now, as far as a biotrickling filter, the process parameters that we're going to monitor, these are the additional process parameters, because all the process parameters of a biofilter, the gas flow rate, we would monitor that. But now we're also going to be looking at the recirculation rate. The recirculation rate is going to be closer to the 1 gallon per minute per foot squared for the biotrickling filter or for a bioscrubber. And the biotrickling filters are continuously irrigated. And this goes back to that what we're relying on here is that these compounds are going to be more easily water soluble. Blowdown is also going to be monitored with a biotrickling filter. And this is just to assure ourselves that the system is going to remain healthy. We need to make sure that the byproducts from the biooxidation do not build to an inhibitory level or toxic level. And therefore, we're going to drain part of the sump or send the part of the sump to drain and add fresh water. And pH and conductivity are two parameters that are used to signal that a blowdown should occur. As far as pH is monitored just to make sure that the environment stays where it needs to stay. And generally speaking, for most industrial applications, It involves the mitigation of organic pollutants, and then these organic pollutants will be treated with the heterotrophic bacteria that Thomas had talked about earlier. And these bacteria operate in the 6 to 8 pH range. Most municipal applications, on the other hand, are treating non-organic compounds such as hydrogen sulfide or reduced organic sulfur compounds. And these reduced sulfur compounds are biologically oxidized by the autotrophic bacteria. And these autotrophs thrive in an acidic environment in the 1.5 to 2 range. And then I think it's interesting to note that these autotrophs actually are generating sulfuric acid as they oxidize reduced sulfur compounds. And again, then we blow down then just to make sure that they don't produce too much acid. Now, and then conductivity, like pH, can be used then to signal that a blowdown should occur, and that's more for the industrial applications that we will use conductivity. And then nutrients is the final process parameter, and these are biological systems, so we need to make sure that the two main nutrients that we make that we want in the system are phosphorus and nitrogen, and they are required in order for the biology to do what they need to do. And normally once a week sampling is sufficient in order to take a grab sample from your sump or from the recirculation line and have that measured. You can either use field test kits, such as a hot kit, to assure yourself that there's sufficient nitrogen and phosphorus in the system, or you can have those samples analyzed at a lab. And you can see that the little nutrient tank in the right, that is actually then, provides our storage where then we meter in the nutrients into the system. And it can either go into the recirculation line like it's shown here, or sometimes they're added right into the sump. And then the next, as far as this is talking about hybrid systems and some of then the equipment that we end up monitoring and using. Whether it's a vertical system, you can see, and again, I guess if you squint, that we do have the two rotating pieces of equipment are the exhaust fan as well as the recirculation pump, and that would be the same for either one. So, and with the as far as a biotrickling filter system, the fan and the pump are going to constitute the majority of the installed horsepower. This is where if you want to figure out your energy requirement, it's going to be because of the fan and because of the recirculation pumps, and that's what we're seeing here. Again, the two main pieces of equipment for a biotrickling filter, and a biofilter would just have the fan. But here's our hybrid system. For the hybrid biofilter system, we take advantage of the benefits of the biotrickling filter, which is the first chamber, and couple it with the biofilter, which is the second chamber. And then you can see the air travels in a countercurrent manner in the first chamber, whereas the airflow was co-current in the irrigation spray in the second chamber. And in the first chamber, this is where the overwhelming majority of the water-soluble compounds are oxidized. The chamber is filled with fixed structured media for biofilm attachment, and the continuous spray from the sump scrubs the organics into the water for treatment by the bacteria. Nutrients then are added to the sump and distributed then via the recirculation spray. The media in the first chamber is fixed media. The vertical flow media has superior biosolids flushing parameters, and this media, the media itself, I'll show you in the next slide, it's located above the grating. As shown in the photo on the right, the media is supported off the floor of the biofilter to provide a plenum for air distribution. The picture on the left shows the fixed media loaded in the first chamber biotrickling filter, and the random packing media, the white media, in the second chamber, which is then the biofilter. The second chamber acts more like an enhanced biofilter and is filled with random or dumped in packing. Some of the random packing is filled with compost. This chamber is irrigated intermittently in order to optimize the formation of fungi that, together with the bacteria, removes the more recalcitrant and harder to degrade VOCs and THCs. The intermittent irrigation is the source of nutrients for this biofilm as well. These photos show the random packing that is in the second chamber biofilter. The structure of the packing helps eliminate compaction, and also the compost. Some of this media is filled with compost, and that provides a good home, if you will, and optimizes fungi formation.
Thank you, Vern. We're getting down to the end here, so one more quick poll question, and we'll pass it back to Vern. Vern, you might need to do some high level on the end of these slides. We're down to about 4 minutes for the rest of the presentation. So where can biofiltration systems be used effectively? And I'll give you guys all a couple minutes here. We've got the wood industry, the paint industry, food and beverage, semiconductor and solar, or all of the above. We'll just let everyone do this real fast. We'll take a look and see if you guys picked up on that from one of the earlier slides. All right, let's see. Good job, everyone. Yeah, it's all of the above, really. I mean, there's a couple industries that certainly have seen in more than others, you know, as Thomas had said, wood industry and paint industry, but you really can use it in all of these. It just really depends on the application and parameters that you have in terms of size and structure. So good job, and we're going to give it to Vern here to take us to the end.
Very good. Thank you. And this, what we're showing here is this is the second chamber, which would be the biofilter chamber empty, and then we have another one where another photo here showing it filled. This is, we use mist eliminators between the two chambers, and this provides the opportunity, or just prevents any overwatering from that first chamber biotrickling filter to the biofilter. So conventional equipment is used there. This is just a simple chevron blade style mist eliminator is used in between those two chambers so that we don't disturb then our biology in that second chamber. The process parameters that we've identified with our piloting and then that we want to control, pH, conductivity, temperature, and quite often that's done with just a PLC. You know, and instrumentation that is used for biofilters, biotrickling filters, it's standard instrumentation, temperature sensors, pH transmitters, so all very, very standard. What's nice about, you know, biofilters, we talked about it, Thomas already mentioned it, green technology. There's no NOx production. There's a reduction in CO2, so that's very important to remember and to consider. A true advantage, truly a green technology that way. And then looking at this slide then is a comparison of the various technologies. And I've got a lot of information on here. I'm just going to say that as far as biofilters are going to be lower in energy compared to many of the other technologies, especially and the fact that with the low energy, and let me show this slide here, we have, this is a comparison of 165,000 ACFM emission stream, and we looked at both, you know, biofilters, biotrickling filter, and a thermal oxidizer. And as far as the cost, you can see that the cost of the energy for the thermal oxidizer outweighs then the two biooxidation systems. And the biotrickling filter, which does have the biofilter, which has a longer detention time, and we are able to get more of the VOCs there is a little bit more energy required for that, reflected in that OpEx cost. But you do get some additional VOC degradation with that biofilter and the longer detention time. The biotrickling filter, much shorter detention time, so you're irrigating less, and so you save some money. The RTL, though, has great performance as far as VOC and the HAPs, which is the what we'll quantify as water-soluble compounds. And here's just a photo of a completed system. Now we're at the questions.
Thank you, Vern. Thank you, Thomas. This is great. And we actually are a little bit over, so we're going to do a couple quick questions. But just a reminder, for the PDH, if you are here for that, you need to take that quiz, and you must pass it with 8 out of 10 and be present for at least 50 minutes of the presentation. You can always go back with the link that you have and rewatch it if you are missing some of the time. We will stay live for another 30 minutes after we go quiet, but you'll still be able to do things on the presentation. Just a reminder, the 2 last widgets are the ones that you need to focus in on, and once you have everything completed, you will be able to print out your certificate. And let me just hit a couple of questions here real quick. Just give me a second here to post them to the screen. So first question, normally does the blowdown require further treatment?
Vern, do you want to answer that? I think I'll probably speak to that best.
I'm sorry, what was the question, Mary?
Normally does the blowdown require further treatment?
Yes. I'm going to say normally we're going to have to look at that blowdown. Either it's going to be sent to a POTW, publicly owned treatment works, to a local wastewater treatment plant, or where it would be treated then later, or you're going to have on-site wastewater treatment. So, yeah.
Okay. And let's just do one more. And again, if you asked a question, we did not get to it, we do reply to all of them. So don't worry about it. We will get to your question here after if we can't do it. And we'll do one more here and then go quiet. So. And it's not pushing to the screen, so give me just a second here. Okay, so EBRT dependent on the most recalcitrant compound in the mix. Okay, too many acronyms for me. Can anyone here on the team help?
I think we would answer that as yes, right, Tom? It is. It's dependent on the most recalcitrant compounds.
Yeah,
EBRT,
it's exactly right.
Time. Mm-hmm.
Yeah, we would look at the emission stream and design the size for the most challenging compound your permit requires. Sometimes the permits don't always require getting everything, and so there you might be able to work with your requirement to figure out what makes the most sense, right? But as Vern mentioned earlier, that second chamber can be quite large if needed, if you have to get everything or most of everything.
Okay, excellent. Well, thank you everybody for attending. We really appreciate it. We do have several more events here planned. We have events in April, May, and June, and you can find a couple of the registrations are already up on CECOcertified.com, and we will be sending out invitations for those as well in the future. Again, thank you for attending. Thank you, Vern and Thomas, and we hope you have a wonderful day.